Welcome everyone. Thank you for tuning in. We are very happy to have Kateryna Tatarko today from University of Waterloo. She's gonna tell us about ellipsoids and their dual volumes.
Thanks. Yeah, so thank you very much for the invitation. I will be talking today about joint work with Sergei Miroshnichenko and Vlad Yaskin. So before I get to the main topic, the main topic is determination of ellipsoids by their dual volumes. I would like to talk a bit about motivation, so where we came up with this question. So the motivation came from the question about the classical intrinsic volumes of ellipsoids. So let's start with just to remind about the intrinsic volumes. So let's start with the classical Steiner formula that says that for a convex body K and non-negative parameter T, it gives the expansion of the volume of the outer parallel body of body K, that is the Minkowski sum of body K and its scale and the scaled ball, unit ball. Then the volume of such outer parallel body is a polynomial in parameter T. So then the coefficients that arise in this polynomial is called intrinsic volumes. And with different normalization, they're also called Kramers integrals. So these quantities carry some information about the original body K, and in particular, some of them have specific geometric meaning, such that the zeroth coefficient is the volume of the unit ball, the first coefficient is up to a constant mid-width of the body K, the second last coefficient is a multiple of the surface area, and the last coefficient is just the volume of body K. So basically, if we look at this formula in the following way, at the Steiner formula in the following way, that for a given body K, I can put in a correspondence the sequence of its intrinsic volumes. So then I can ask the following question. So can I say something about the shape of the body based on its intrinsic volumes? So can I determine a convex body by its Steiner polynomial? And in general, the answer is no. So one can construct some example in the higher dimensions, but even on the plane, this is not true. So I can look at this triangle that is formed by 4 equilateral triangles, and then I can rearrange this 4 equilateral triangles in such a way that I have this parallelogram, but both of these bodies will have the same area and they have the same perimeter, but they do not coincide. So their intrinsic volumes are the same, but they do not coincide up to any isometry. So of course, in general, the answer is no, but can I restrict somehow this question in such a way that I can expect to get the positive answer? So can I consider some specific maybe families of bodies in order to get the positive answer in this direction? And the naive way to think about it, okay, since I have n intrinsic volumes, so I have this n conditions. So for me to hope that I can solve this system of these relations here, I maybe want to try to consider n parametric families of convex bodies, that are those convex bodies that are defined by n parameters. And the supporting example in this direction is if we consider rectangular parallelepipeds. So rectangular parallelepipeds are defined by their side lenses. So they're defined by their n parameters, which are their side lenses. And if we compute intrinsic volumes of rectangular parallelepipeds, then each intrinsic volume is just elementary symmetric function in terms of the side lenses. So then I can take these intrinsic volumes and consider the corresponding polynomial where these intrinsic volumes are coefficients. By Vieta's theorem, I can conclude that I can determine the side lenses uniquely from this polynomial. The side lenses will be just roots of this polynomial due to Vieta's theorem. So indeed, in case of rectangular parallelepipeds, we can consider they will be determined by the corresponding intrinsic volumes. So another family, which will be the family that we will be interested in during the talk, will be the family of ellipsoids. So throughout the talk, we will be considering ellipsoids that are centered at the origin and whose semi-axis aligned with the coordinate axis. So the ellipsoids also defined by n parameters, which correspond to their semi-axis. And Gusakov and the projects conjectured in 2017 that if we consider two ellipsoids such that the intrinsic volumes are the same, then it implies that the two ellipsoids should be the same, or congruent, which means that they coincide after an isometry. So in two-dimensional case, this result is true, and it's not too difficult to show that it's true. In three-dimensional case, it was recently proved by Petrov and Tarasov, but in high dimensions, the problem still remains to be open. So what we are interested in, instead of considering this conjecture about classical intrinsic volumes, we would like to consider a similar question about dual volumes. But before I get into that, so for now, I will not be talking about this particular conjecture, but in the end of the talk, I will come back to it and say a few remarks, how the dual case connected to the classical case. All right, so before we formulate the main question, let's recall just some notions. So the first, in the dual Brunn Minkowski theory, we will be working with star bodies, and the radial function of a star body K is defined by defined in the following way as the following maximum over all non-negative parameters. Then for two star bodies K and L, we can define a new body that is the radial sum, which is again will be the star body whose radial function now defined as the linear combination of radial functions of original body K and L. So basically what we're doing, we're taking a body K and we want to add to it the unit ball. Then we fix the direction theta, we take the radial function in the direction theta of body K, and we add to it the radial function in this direction of the unit ball. Then the corresponding this new the result will be the radial function in the direction theta of this new body, which is, we call the radial sum. So then, by analogy with the classical Steiner formula, there is a Steiner formula in the dual Brunn Minkowski theory. So here now, instead of convex body, we consider star body K, and instead of Minkowski addition, we now take the radial addition. So the dual Steiner formula says that the volume of this radial sum of body K and the scaled ball, again, is a polynomial in parameter T. And the coefficient that arise in this polynomial now called dual volumes. So the nice thing about dual volumes that they actually have a nice integral representation. So they can be written as integrals over the sphere of powers of radial function. And it's worth noting that both intrinsic volumes and dual volumes are invariant under orthogonal transformations, but intrinsic volumes are also invariant under translations, while dual volumes actually depend on the choice of the origin. Okay, so now by analogy with the classical case, I have the dual Steiner formula that gives me the correspondence for each star body K. I get the sequence of dual volumes. I can ask the similar questions. Can I say something about the body K based on the sequence of dual volumes? And now we will not be looking among all star bodies, but we'll be focusing on the family of ellipsoids. So can we say something about, can we determine ellipsoids based on its dual volumes? And we found the positive answer here. So indeed, if we consider two ellipsoids centered at the origin, such that their sequence of dual volumes coincide, then these two ellipsoids are congruent. And okay, so this is the main result. And now I will say a few words about the proof of the result. All right, so in order to prove the theorem, we need the following representation of dual volumes. We need the following lemma that gives the dual volumes as integral over the positive real line of the following function. And here, it's important to note that the following formula is actually valid for any index I between 0 and n. So for any real number between 0 and n. And we exclude case 0 and n because case I is equal to 0 corresponds to the volume of the unit ball, which doesn't give any additional information about an ellipsoid. And the case I is equal to n corresponds to the volume of ellipsoid. And the volume of ellipsoid is just the product of, up to a constant, it's the product of its semi-axis. So, but the remaining dual volumes can be written on, when indices come from this interval, can be written in the following way. So let's sketch the proof of this. So it basically relies on the integral representation of the dual volumes in terms of the integrals of powers of radial functions. Then we use the relation between the radial function and Minkowski functional, that is, they are reciprocals of each other, which led us to rewrite this integral in the following form in terms of the Minkowski function of the ellipsoid, which we can write now as a square root of the sum here. So then we can work now with this last integral. So first, using polar coordinates, one can show, one can pass from this integral over the sphere to the integral over Rn. And once we do this, we'll also rewrite this negative powers of the Minkowski functional here as the following integral over the non-negative real line. So to check this relation, one just can use the following change of variables of this integral. And then combining these two formulas together, we get that the dual volumes of ellipsoid can be written now as the integral over the positive real line and integral over Rn. Now, when I take a closer look at this integral over Rn, I can see that I can actually write it as a product of iterated integrals with respect to each variable xi. So I can, if I do this, I get the product of this integrals with respect to each variable xi, and this integrals is just the Gaussian integral with the following constant for each of them. So computing each of these Gaussian integrals here, we get the needed representation. So now once we have this in hand, we can try to prove the theorem. So what we start with the given n conditions. So we know that the dual volumes of the two ellipsoids coincide. Using this integral representation, which we just proved, we can rewrite first n-1 conditions in such integral form. And the last condition, when I is equal to n, corresponds to the just equality of volumes of two ellipsoids. So n's the dual volume coincides with and intrinsic volume, which is just the classical volume of the body. So up to some constant, the volume of ellipsoids is just the product of semi-axis. So the last condition tells us that the products of semi-axis for two ellipsoids are the same. So we keep this condition in mind, but first we will work with the integral, this n-1 integral conditions. So we will simplify in such a way that we move two integrals to one side, collect terms, and the function that stands in front of powers of u, we call it the f capital. So this is just a difference between these two fractions. Then all this n-1 conditions can be rewritten in this form. So we have that the integrals of a positive real line of the following expression should be equal to 0. But what does this mean? This means that I can actually consider any polynomial of degree at most n-2, and degree at most n-2 because we have power of u here i-1, and the largest index I which we can take is n-1. So the previous n-1 conditions imply that for any polynomial of degree at most n-2, we have the following equality. Then, okay, so how can we analyze it? If we show that function f capital has at most n-2 positive real roots, then we can choose this polynomial in such a way that its roots, that it changes sign exactly at this numbers here. If we do, so I assume for now that function f capital actually has at most n-2 positive real roots. So then by picking this polynomial in the following way, we know that the product of the polynomial p and function f capital has determined sign. So it's either everywhere positive or it's everywhere negative. But then this equation here will imply that the function f capital should be identically equal to 0. Which now, using the representation of function f capital, playing with it around, it actually implies that the sequence of semi-axis coincide for both ellipsoids. So, and here we are done. The only thing which we are missing here is the fact that this function f capital actually has at most n-2 positive real roots. So let's try to show it. So in order to show that f has this number, at most this number of roots, we need to solve this equation. And again, using the expression of f capital, putting the fractions on the two different sides, taking reciprocals, squaring both sides, we can rewrite it in the following form. Now we can expand the left-hand side and right-hand side in the following way. So I will separate the constant term, which is in both cases is equal to 1. I will also separate the largest power of u on both sides, which will have this coefficient, the reciprocals of the squares of product of semi-axis. And the remaining term I will just put in some, this will be just some polynomial, but I know that this polynomial will be of degree at most n-2 in this parameter u squared. So then I can simplify, so the constant term will cancel out. And here we recall that we haven't used our last condition. So we have that the volumes of two ellipsoids also coincide, meaning that the product of semi-axis of them are the same, which led us to cancel out the term with the highest power of u. And eventually, by simplifying, we reduce it to the following equation. So which tells us that indeed f will have at most n-2 positive real roots, since this polynomials are of degree at most n-2. And we are done. So we're done with the main theorem. So what we got, we indeed showed that if we take the dual volume that arise in the dual Steiner formula, and if we take two ellipsoids such that these dual volumes are the same, then these two ellipsoids should coincide. But in fact, we can show something more. So instead of looking only at dual volumes that come from the dual Steiner formula, we can actually look at this integral representation of dual volumes. So if we look at this integral on the right-hand side, it makes sense for any real parameter I. So if I, instead of thinking about dual volumes as those that are coming from the Steiner formula, only those with integer indices that are coming from the interval between 0 and n, I can think about dual volumes defined by this integral representation. So then instead of taking the previous sequence of dual volumes, I can take any n-tuple of dual volumes whose indices coming now from the larger interval. And for now, let's focus on the interval between 0 and n. So in a few slides, I will talk how we can get outside of this interval. But for now, we will just consider n-tuples of dual volumes whose indices lie in this interval. Then again, we can show the similar results. So again, if we take two ellipsoids such that now any n-tuple of dual volumes whose indices are coming from the interval between 0 and n are the same, then it implies that ellipsoids should be the same. And in order to prove this result, we can follow the similar scheme as before. So at the start, we basically do the same thing. We have our n condition, and we can rewrite them in this integral form. The only difference here that now the powers of u are not necessarily integers, because our indices are not necessarily integers anymore. But our goal to conclude, if we able to conclude that function of capital is identically equal to 0, then we can proceed as before. Then we will be able to show that the semi-axis coincide, because that's what, if we analyze the equation, then that's what it means. So in order to show that function of capital is equal to 0, that's where we need to make some adjustment. And in order to do that, we will use the lemma due to Eskenazi, Steiner, and Koch, which says that if we consider continuous function that changes its sign at most n-1 times, on the positive real line. And if there exist and distinct real numbers pi's such that such integrals equal to 0, then the function f is identically equal to 0. So in order to apply this lemma, we have to distinguish two situations. First of all, if among these conditions that we have one condition that corresponds to equality of volumes. In that case, we can proceed exactly as we did before. So using the equality of volumes, we can show that F capital has at most n-2 positive real roots, the same way as we just done a few slides ago. And what we have here, so this one condition corresponds to equality to volumes, just gives us that the products of semi-axis coincide, but the remaining n-1 conditions will be written in this integral form, and all these integrals will be equal to 0. So we have n-1 integral conditions, and f can have at most n-2 positive roots. So we can apply this lemma, and this lemma will imply that f capital is equal to 0. On the other hand, if we don't have equality on volumes of two ellipsoids, then by the same previous argument, we can show that f capital has at most only at most n-1 positive roots, because the largest power of u will not cancel out. And we will have all n integral conditions in this form. So again, we can apply this lemma, and it again will imply that f capital is equal to 0. So in any case, we applying this lemma, we can conclude that f capital is identically equal to 0, which gives us that the semi-axis of two ellipsoids are the same. Okay, so which finishes the proof here, and saying that, okay, we can now take any n-tuple of dual volumes, but we had the restrictions on indices of this n-tuple of this dual volumes. Now, how can we get the result for a larger set of indices? Unfortunately, when we go outside of the interval from 0 to n, the previous representation lemma that we had just doesn't work. The integral there will be not convergent if the index I lies outside of the interval from 0 to n. So once we go outside, we need to somehow adjust our representation, and we can do it by trying to regularize our integral. So in order to do that, we can apply the analytic continuation technique, and each time we get the index outside of the interval 0 to n, we can write the corresponding representation. So in this case, I will just present two special cases. So one can generalize this lemma, and it's written in the paper in the more general way how we can write the representation when I lies outside of the interval 0 to n. But here I don't want to get into all the technicalities, so I just want to give this specific example, which I will use later on. So if we have index I that belongs now to the interval from -2 to 0, then the representation of the dual volumes in this case is similar, but now we need to adjust it a bit, and the following adjustment in this case is just subtracting 1 here inside the bracket. And if index I lies between n and n+2, then the representation of the dual volumes can be written in the following form, and now we adjust by subtracting the following term, which involves the volume, basically, which involves the product of semi-axis. Okay, so this was the first difficulty. And the second difficulty, if we want to obtain now the result for any n-tuple where the indices of these dual volumes fall outside of the interval 0 and n, we also, and if we want to get the positive result for the previous question, we actually need to fix some certain conditions among our relations that we start with. So again, this theorem can be generalized, can be written in more general way when the indices of dual volumes fall to the larger interval. But here, just based on the previous representation, I will show a specific example. And again, I will just use this theorem later on. So if we have two ellipsoids centered at the origin such that now here we want to ask that their volumes are the same, but the remaining n-1 conditions, I can take dual volumes of any order when their orders come in now from this larger set of indices. So the only difference here that I want to require that their volumes are the same. Then I can answer that yes, indeed, in this case, again, the two ellipsoids will be the same. So just a quick, I would just want to give a quick explanation why actually we need to require now this equality of volumes in this case. So in order to proceed as before, again, we start with our now n-1 integral conditions, because the first relation is just equality of volumes. And what we want to write them in this form. So we want to write them that these integrals are equal to 0. If we do this, then we can apply one of the previous lemmas and can show that f capital is identically equal to 0. But in order to write them in this form, now we need to be careful where the indices of these dual volumes are coming from. So if the index of dual volumes lie on the interval from 0 to n, then we can proceed as before, and we know that we can write it in this form. We can use our first representation lemma, and everything's fine. Now, if index I lies outside of that interval, so first, if it belongs to interval from -2 to 0, we can use this first expression. When we move both integrals to one side, the one here, this constant, just cancels out. So again, we will be able to write them in this form. The difference is in the case when the index will be in the interval from n to n+2, then we will need to use the Polovin representation. And in order to get rid of this additional term in this case, that's where we use the equality of volumes. Since volumes of two ellipsoids are the same, then the terms here, the product of semi-axis for both of the integrals will be the same. And the term will cancel out, and again, their relation can be written in the integral form. Okay, so this more or less finishes completely the case of the dual volumes. So indeed, we can consider any n-tuple of dual volumes, so we can consider dual volumes that coming from the dual Steiner formula, and they will determine the ellipsoids unit. So now what I would like to talk in the end, how this result is connected to the classical question. So the question which was asking about classical intrinsic volumes. So first of all, let's start with the three-dimensional case. And as I said before, that Petrov and Tarasov proved that if we have two ellipsoids such that their mean width, surface area, and volumes are the same, then these two ellipsoids should be congruent. So they proved their result using differential geometry tools. But what I would like to present here is the analogous proof that follows actually from the dual case. So in order to prove the Polovin theorem using the dual result, we can make use of the following two formulas that relate. First one relates intrinsic volumes of ellipsoids and their polars, and the second one in a similar way relates dual volumes of ellipsoids and dual volumes of their polars. So then we can express mean width just by using the representation of mean widths in R3 as up to a constant minus first dual volume of the polar corresponding ellipsoid. And then using the following one of these formulas, we can rewrite it as the ratio of the forced dual volume and the volume of the ellipsoid. And similarly, we can deal with the surface area. So we can write surface area using the first formula as the product of the volume and the mean widths of the polar of ellipsoid. And then we can deal with the mean widths of the polar the similar way as we did here in the first equality case. So we can write it up to a constant as a product of the volume and the minus first dual volume of ellipsoid. So using these two relations here, we see that to know mean width, surface area, and the volume, it's enough to know the forced dual volume, minus first dual volume, and the third dual volume. So basically, we have a correspondence here between this triple of intrinsic volumes and this triple of dual volumes. But since we in three-dimensional case, and among this triple of dual volumes, we also have the volume, just the third dual volume. We exactly in the situation of this theorem here. So we have equality of volumes, and two other dual volumes, the indices are taken from the interval between -2 and 5. In our case, these are dual volumes with indices -1 and 4. So by the previous theorem, we actually know that such triple of dual volumes determines ellipsoid unique. So the nice thing that in R3, there is actually this nice relation between the intrinsic volumes of ellipsoids and dual volumes of ellipsoids. But unfortunately, when we go to the higher dimensions, there is no such nice correspondence between classical intrinsic volumes and dual volumes. So we were not able to get the answer to the entire conjecture. But by using the dual result, we were able to make a slight progress towards the classical conjecture that concerns ellipsoids of revolution. So if we consider ellipsoids of revolution and consider the question for the classical intrinsic volumes, then we can actually obtain some partial results. So the first result says that if you have two ellipsoids such that the following triple of intrinsic volumes are the same, so the ellipsoids have the same volumes, the same ith intrinsic volume and n minus ith, then the ellipsoids should be the same. So in order to prove the results of ellipsoids of revolution, we make use of the nice formula which can be obtained for intrinsic volumes of ellipsoids of revolution in any dimension Rn. So indeed, if we, in the case of ellipsoids of revolution, then intrinsic volumes can be represented as this integral over the sphere, which depends on on the two distinct semi-axes, A1, I call it here A1 and AM. So, but unfortunately, if we are not in the case of ellipsoids of revolution, then the formula here for intrinsic volumes becomes more complicated, which makes it more difficult to deal with. But in the case of ellipsoids of revolution, it has a nice form, and we extensively will be using it in the proof of the theorems here. So the only one remark which I want to say before proving the following result, that if you look at the ellipsoids of revolution, they actually determined by the two distinct parameters. So they have two semi-axes that are distinct. In this case, I call it A1 and AN. But in the theorem, we ask for 3 conditions instead of 2 conditions. And it turns out that, unfortunately, 2 conditions in this case is just not enough to determine the ellipsoid of revolution. And it follows from these observations, if we fix the volume of the ellipsoid, and without loss of generality, we can say that the volume is the same as the volume of the unit ball, then we get the following relation between A1, A, and N, which led us to express one of the semi-axes in terms of the other. Then if I look at any other ith intrinsic volume and use the previous formula, I get the function only in terms of one variable A1. But if I look closely at this function, I can note that if I make A1 very small, then the intrinsic volume here will be very large, and vice versa. If I make A1 very large, the intrinsic volume still will be very large. So in terms of the graph of the function, it will look something like that. So when A1 is small, Vi is large, and when A1 is large, then Vi is large as well. So based on this, we can see that we can actually find 2 different ellipsoids with prescribed values of these 2 intrinsic volumes. So it turns out that to ask 2 conditions in this case is just not enough to determine ellipsoid of revolution unique. But if we ask for such triple of relations, then we're good. Then we can actually show that these 2 ellipsoids should be the same. Okay, so let's look at the proof. So again, without loss of generality, we can assume that the volumes are the same and they equal to the volume of the unit ball. Then this just allows us to rewrite semi-axis of both ellipsoids only in terms of one variable. And our goal is to show that the semi-axis corresponding to the first ellipsoid are the same as for the second one. So we used already equality of volumes. What is left quiz, we're left with the two additional conditions: the equality of ith intrinsic volumes and of n minus ith intrinsic volumes. Now, using the formula for intrinsic volumes of ellipsoids of revolution, we can actually note that we can rewrite this as the relation between minus first dual volumes of two ellipsoids. And similarly, we can deal with the second condition, but first we can just write that this is minus first dual volumes of the polars of two ellipsoids. And then using the formula that relates dual volumes of ellipsoids and their polars, we can rewrite it as the equality of n plus first dual volumes. Okay, so what we have now, we have these two condition on dual volumes. We can rewrite in this integral form using the previous representations. But now function of capital will depend on this parameters a1 and b1. And in order to conclude the result, we again need to show that f capital is identically equal to 0, which will imply that a1 is equal to b1. But to do that, we need to show that f capital has at most one positive. And this is not too difficult to do. Just by examining this function, we can show that it will have at most one positive, which finishes the proof in this case. Okay, and what we also got, we've got the second partial result, which concerns ellipsoids of revolution. So which says that if we look only at even dimensions and fix such triple of intrinsic volumes, so the volume, the middle intrinsic volume, and any other ith intrinsic volume, then we can determine ellipsoids of revolution uniquely. So let's look at the proof. So again, using the volume condition, we can get rid of one of the semi-axis, or rewrite the rest only in terms of one semi-axis. Then this intrinsic volumes of order n over 2 now can be written in the following form, which depends only on one of the semi-axis, only on this parameter a1. And if I look at this integral here, I can make a few observations. So the first observation is, if I check the denominator here, this is actually increasing and decreasing function in terms of parameter a1 on the interval from 0 to 1, and increasing on the interval from 1 to infinity, for any u, for any non-negative u. So which will imply that the entire integral here, this entire function v n over 2, also will be decreasing and increasing on the corresponding intervals. And the second observation is that this integral is actually invariant under the following transformation. So indeed, if I change a1 to its reciprocal, this integral will not change. So they will just, these brackets will just change places, but it doesn't matter. So the integral is invariant under this transformation as well. So then these two observations will imply the following. So the first one will say that, okay, as before, with fixed volume and the n over 2 intrinsic volume, we can find at most two different ellipsoids with such prescribed values of these two intrinsic volumes. And the second observation here say that since this function's invariant under the following transformation, we'll say that these ellipsoids must be polars of each other. So in fact, we're in the following situation. We're in the situation either these two ellipsoids are the same from the start, which is completes the proof, so then we are done, or they will be polars of each other. So what if they are polars of each other? If they're polars of each other, then we still have the last relation. So there, we still know that the ith intrinsic volumes of the ellipsoid, and it's now dual, is the same. But this condition implies that the polar relation is also true, that n minus ith intrinsic volumes of this ellipsoid and its polar are the same. So what then we are in the situation of the first theorem regarding ellipsoids of revolution, because we have that the following triple of intrinsic volumes coincide. The volumes are the same, and these two intrinsic volumes are the same. The first theorem tells us that in this situation, such ellipsoids must be the same. So, but they are the same. Their ellipsoid is equal to its polar if it's a ball, and which will imply that the second ellipsoids also should be the pole. So in this case, again, both ellipsoids should be the same. They should be the balls, but they should be the same, which finishes the proof in this case. So even though we were able, I will go back a bit back. So even though we were able to obtain these partial results about ellipsoids of revolution, but even here, many other cases are still open, because we asked for this triple and we actually relied to have, in this case, that among this triple of intrinsic volumes, there is a volume of ellipsoid, and similarly to the previous case, we rely that among such triple of intrinsic volumes, there is a volume of ellipsoids. So there are still a lot of open cases, even for ellipsoids of revolution, but of course it would be nice and interesting to see whether the actual conjecture about intrinsic volumes of ellipsoids is true as well. Okay, and I will stop here. Thank you.
Thank you, Katya. Are there any questions?
Hi.
Hi.
Thank you for your talk, Kateryna. Yes, I can just haven't understood one technical point on your page 20.
Okay.
Just before here, yes, because how did in the second equivalence
Here
there is no I?
Yeah, there is no I, because
right.
so it relies basically on this formula, right? So in fact, it's even in this form. So I can write so assuming that I have equality of volumes, right? I can write the I's intrinsic volume in the following way, but then this one will just be equal to the minus first dual volume.
Yes. Okay. Okay.
So this, yeah, so here, so yeah, so it doesn't depend. And then the second one follows because I just switch I with n minus y's, so they just switch places, and I get just the reciprocals of A1, which gives me the minus first dual volumes of the polars of ellipsoids instead of just ellipsoids.
Yes, yes. So yeah, okay, thank you. And another one. So as you said, there are many non-resolved cases. And for example, so you have you fix the volume and then the ith and the n minus i's, and not I and j, for example.
Yes, exactly. So just if it's just j, at least we were not able to get the result.
Okay. Okay.
Yeah, so here it's kind of we fix volume and then the symmetrical, right? Like from one side and from the other side.
I see. Yes. This is very strange. Yeah. So there are many beautiful formulas for ellipsoids. I see. But not enough to do everything yet.
Yeah. Yeah.
Okay. And for parallelotops, for the dual part, you
for the dual part,
do it, or it's not important, or?
So it's unfortunately also not clear how to do it. So you can consider for any LP ball, right, like the scaled LP ball, so you can make it that it contain depends on n parameters. But unfortunately, yeah, we also were not able. It becomes very technical, and it's not clear how to analyze that case as well. So it's also for the dual case. There actually for any scaled LP balls, it's not clear. It would be also very interesting to know actually what happens.
L1 balls also. Yes.
Yeah, L1 ball.
Yes.
Even though there's like also some formulas for L1 for cross polytopes, and
yes,
it just becomes too complicated and not clear how to. My guess is that it probably should be the same as for ellipsoids. The question is how to get.
Okay. Thank you. That's all for me.
And any other questions?
Hi. Thank you for your talk. Your proof was quite cool. I've got another question about this main conjecture. Do you have any counterexample which is symmetric to this main conjecture of Gusakov and Zaporožec?
No, we don't have. No.
Okay. And for your dual conjecture, do you have any counterexample?
No.
Okay, because what perhaps may be crucial is that ellipsoids are their own linear images. So maybe if you take a symmetric body and some linear images of it, one linear image, and assume that all intrinsic volumes or dual intrinsic volumes are equal, maybe it means that this this linear operation is an isometry. Okay, it might happen, but I don't know. I don't feel dual intrinsic volumes, so
yeah. But that's also, yeah, it would be also interesting to check. But that's true.